This section defines what a nanorobot is. A nanorobot is defined by function. Whatever it is built from, any active structure that actuates, senses, manipulates, propels, signals, computes, or swarms at the nanoscale counts as one. The material never enters the definition. That single move, an object is what it does, is the choice the whole chapter turns on. It lets 4 incommensurable substrates sit under one name: large nanomanipulators, protein and DNA machines, magnetically steered particles, and harnessed bacteria. What unites them is shared behavior rather than shared material. What no substrate yet reaches is the whole capability set in one artificial autonomous body. The authors call that gap the Mount Everest of nanorobotics. The chapter's job in the book is to draw this boundary by function and to mark the unclimbed peak. This section fixes what the word nanorobot means for the whole book. A nanorobot is a functional category rather than a shrunken machine. It is anything that actuates, senses, manipulates, propels, signals, computes, or swarms at the nanometer scale, defined by what it does, never by what it is made from. The chapter then partitions the field by substrate rather than by function. The groups are large manipulators with nanoscale reach, protein and DNA-based bionanorobots, magnetically guided particles, and bacteria-driven systems. The move worth keeping is that capability is the invariant and material is the free variable. So a scanning probe tip and a flagellar motor land in one taxon because both act at scale, however unlike their construction. Everything the later chapters build inherits this substrate-blind framing. Substrate-blind framing. This section explains the chapter's primitive, a flexible beam whose bending is the reading and is also the push. That collapse of 2 rolls into one is the whole idea. At the nanoscale, the tool that senses a surface and the tool that moves an object stop being distinct. An AFM cantilever's deflection maps topography under light contact. The same deflection, held to a target force, becomes controlled manipulation of a nanobject. 1 beam, 1 signal, 2 functions. Jalili frames this as the sensing and manipulation branch of scanning probe, microscopy. The probe scans the surface, and the interaction yields a signal. He deliberately sets aside the more versatile nanorobotic manipulators because their sensing is too slow and too blind. The book's wager is this: at these scales, precision comes from a probe that reads by touching and manipulates by the same touch. This section explains how, at the nanoscale, reading a surface and writing to it become a single act. A sharp tip held a few angstroms from a surface couples to it through some force law, a tunneling current, or the deflection of a tiny cantilever. That coupling does double duty. Its strength reports the tip to surface distance, and that same strength, pushed harder, moves the atom beneath. The chapter's move is to see manipulation as sensing turned up. What makes the tip a ruler is the steepness of the law. Tunnel current falls exponentially with separation, so a shift smaller than an angstrom swings the signal decisively. Everything downstream, AFM, force sensing, laser-free imaging, is this one transducer, converting mechanical proximity into a number. This section explains how a swarm of self-organized nanorobots builds a shape that no single robot knows. A swarm builds a form larger than any of its parts. Requich's move is called global to local compilation. You specify the target shape once, a compiler grinds it down into a set of stateless reactive rules, and every identical robot runs those same rules on purely local sensing. There is no boss, no stored blueprint, no global addressing. The prescribed shape lives nowhere as data. It is the fixed point that the local dynamics converge to. From this, self-repair falls out for free. Delete robots, inject faults, and the survivors reconverge to the same attractor, because healing is just convergence run a second time. The inversion that makes this powerful is this. Emergence is normally something you observe after the fact. Here, it is compiled. The desired behavior is specified first, and the local rules are derived to produce it. This part explains how a swarm builds a global shape without any robot holding the plan. No robot holds the blueprint. A prescribed global shape is compiled into a single set of stateless reactive rules. Every robot is identical, running those same rules, reading only its neighbors. The shape is stored nowhere. It is the fixed point that the local rules settle into. Self-repair then costs nothing extra. Perturb the swarm and the same rules reconverge, because an attractor restores itself. That is the chapter's whole move, global to local compilation. It surprises that robustness is not bolted on. Robustness falls out of the attractor's stability. From this, you can predict the rest. Any global target expressible as a stable, fixed point of local interaction needs no boss and no central plan. N needs no boss and no central plan. This section explains how the injected floodwater itself becomes the measuring instrument. Stop drilling boreholes to peer at the reservoir from outside. Seed the injected floodwater with agents small enough to slip through the rock's pore throats, and the flood itself becomes the instrument. That is the whole chapter. Nanotechnology here is a matter of scale. Shrink the sensor until it rides the same water that already sweeps the oil, and it reports from in situ where no probe reaches. Kanjis, resbots, ladder. One axis of autonomy. Passive barcodes merely correlate which injector feeds which producer. Active markers record the environment they pass through. Reactive agents alter transport as they meet it. Sensing and intervention are the same move at rising boldness. The medium carries the eye. As they meet it, sensing and intervention are the same move at rising boldness. The medium carries the eye. This section carries the paradigm of one medium into another. Take the paradigm the rest of this book aims at the bloodstream. Inject a swarm of molecular agents into an interior, too vast and too hostile to probe from outside. Let them map it and act on it in situ, and point it at an oil reservoir instead. That is the whole move. The reservoir is just another body. Kilometers of fluid-filled porous rock at crushing pressure and heat, opaque to any macroscopic instrument. Resbots illuminate the subsurface and reroute its transport, the way a therapeutic nanorobot illuminates tissue. Only the target medium swaps, pore throat for capillary, and the pattern holds. Nanorobotics is domain agnostic, and medicine never held a monopoly on it. This section explains why miniaturization in space robotics has no fixed meaning of its own. Miniaturization is a ratio against the scale of the task. On Earth, the labels micro and nano index a device's size or resolution against the human scale baseline. But space's baseline is orbits and megameters, so the identical physical shrink no longer qualifies. Shrinking components therefore does two structurally distinct things, and which one you get is pinned by what the robot acts on. When the object stays large, as with the ISS manipulator handling satellites, size is frozen and the freed volume, mass, and power by added capability. When the object scales down, too, size collapses at fixed capability. When the object scales down, too, size collapses. One operation, two outcomes selected by the reference frame. E. This section explains why the words micro and nano, as this chapter uses them, do not mean what they mean elsewhere in the book. Micro and nano are relational terms. Each names a ratio to a task's characteristic scale, rather than an absolute size. The book's other chapters silently fix that reference at the human body, so a nanorobot is genuinely nanometric. This chapter swaps the reference to orbits and planetary distances, and the same words slide by many orders of magnitude. A nanosatellite would not qualify many orders of magnitude. A nanosatellite would not qualify as nano by Turing goddess like cease. Once the term is relational, miniaturization splits into two orthogonal moves. The first holds size fixed and spends the freed volume and mass on capability, the way the ISS arm is chained to large payloads. The second holds capability fixed and collapses the size, the way the nanosatellite does. This chapter's place in the arc is to show that the book's central word is frame indexed, keyed to whatever reference scale the task fixes, and not absolute. This section explains the one manufacturing primitive that the whole medical promise of diamondoid nanorobotics collapses onto. The claim is Freitas's. The ceiling on a nanomachine's achievable complexity is set by how precisely you can place its atoms. Design ingenuity is not the limiting factor. Atomic placement precision is not the limiting factor. Self-assembly hopes that parts fall together stochastically. That is fine for simple structures and becomes intractable as intricacy grows. So you replace hope with positional assembly. You pick each molecular part, move it along a controlled trajectory, and set it down, atom by atom. It is the logic of a car assembly line, scaled down to molecules. And you build in diamond, because a stiff, covalent lattice makes both the part and its placement deterministic. Rigidity is what keeps positioning from blurring into thermal noise. The chapter names the field's bottleneck, capability gates application, and the gating capability is atomically precise, rigid, positional fabrication. Why precise, rigid, positional fabrication? This section explains why building a molecular machine of millions of parts requires positional control rather than self-assembly. Stochastic self-assembly caps complexity. Error. Probability compounds with part count, so a thermodynamically driven process cannot reliably build a machine of millions of components. The escape is positional assembly, where every part's position and trajectory is controlled at every instant, pick and place, like a car assembly line. That determinism is what buys reliability at scale. Diamondoid is merely the chosen material, elected because its rigidity yields repeatable mechanical operations. The chapter's whole arc hangs on this single inversion, self-assembly versus positional control. Biology already proves the positional side works. The ribosome places amino acids, one by one from a digital sequence. Complex specified structure demands deterministic placement, never lucky thermodynamics. This section explains how a single scanning probe can act as a many-fingered hand. A single AFM tip pushing a nanoparticle loses it. Off-center contact torques the object away, and recovering it demands a fresh scan. The fix costs nothing physical, Sweep that one tip around a closed trajectory faster than the particle can relax, and time averages the visited points into a standing cage of contacts, a many-fingered hand synthesized from one-fingered hand. The primitive is time division, multiplexing across a timescale gap. When your effector cycles faster than the system integrates, one thing presents as many. Persistence of vision paints a whole image from a single scanning dot the same way. Change the trajectory, change the tool. The hand is software over one actuator, not new hardware. Actuator reprogrammed in code while the hardware stays fixed. This part explains how a single probe can hold a nanoparticle in place. A single tip pushing a nanoparticle loses it. Point contact plus tip position. Drift lets the object rotate off, axis, and slip away. And you only learn about the failure on the next scan. The chapter's move is to time multiplex plurality. You sweep one AFM tip through a predefined closed trajectory, fast enough that the object feels a virtual nano hand caging it rather than a single finger. Spatial parallelism, the many fingers of a real gripper, is traded for temporal repetition of a single actuator. Object closure emerges from a single actuator. Object closure emerges from a path. Here is the generative primitive. When hardware cannot be replicated in time. One end effector, revisited quickly, is many. He caging that simultaneous contacts would do in a real hand. The generative primitive is this. When hardware cannot be replicated in time. One end effector, revisited quickly, is many. This section explains the 8th chapter, Nanorobotic Mass Transport, and why feeding atoms into a factory is the piece that still does not work. Feynman's atom-by-atom factory needs 3 primitives: feeding, positioning, and connection. Positioning and bond formation already work, so feeding is the grand challenge, still running at roughly a billionth of the rate wanted. This chapter is the feeding pillar. Its central move is an isomorphism, a mass network that pipes atoms the way the internet pipes bytes. Bytes, sources of each atomic species, are routed to clients through carbon nanotube channels with mass metered at the attogram scale, that is 10 to the minus 18th power grams. Manufacturing becomes a flow control problem. Yeses, this. The reframe is the whole payload. Matter stops being a sparse surface. You pick one grain from at a time and becomes addressable, continuous flow. Everything downstream is just controlling that pipe. This section explains the central idea of Chapter 8, that manufacturing is a transport problem. Feynman's dream of building matter atom by atom is recast here as a question of transport. The whole chapter runs on a single isomorphism. A mass network processes material atom by atom, just as the internet processes information byte by byte. Carbon nanotubes are the pipes. Attograms of metal are the packets. Manufacturing decomposes into 3 transport primitives: feeding, positioning, and connection. The move that makes this work is treating matter delivery as routing, with sources of atoms wired to clients through channels. The surprise is where the bottleneck sits. Placing atoms and making bonds are both already demonstrated. The bottleneck sits earlier, in feeding the atoms controllably, and current rates run at 1/billionth of what fabrication demands. The frontier is transport. Assembly is already solved. This section explains why putting nanomanipulation inside a scanning electron microscope changes what the tool can do. The move that makes everything else follow is decoupling the sensor from the effector. Atomic force microscope manipulation forces one microcantile ever tip to both see and push, so imaging and manipulating cannot happen at once. You are blind in the instant you act. Put the manipulation inside an SEM, and the electron beam becomes an independent eye, watching at video rate, while a separate piezoelectric arm does the touching. Vision and force now run coordinately rather than in alternation. That single architectural split is what the chapter is for. It buys per object precision at nanometer resolution. The cost is also the boundary that predicts the rest. This is the serial, one-at-a-time pole, chosen deliberately against the fast parallel batch methods, directed assembly, and dielectrophoresis, which trade specificity for throughput. This section explains why nano-manipulation gets easier the moment you stop asking one instrument to both see and act. That split is the chapter's whole move. Atomic force manipulation fails at simultaneity because a single cantilever tips both images, the surface, and pushes the object. The sensing organ and the effector organ are the same hardware, so the instrument cannot watch itself work. Inside a scanning electron microscope, the electron beam sees at video rates, while independent piezoelectric arms, carrying interchangeable probes or grippers, do the pushing, pulling, and soldering. Decouple the observation channel from the actuation channel, and closed-loop visual servoing follows naturally. Yes, well, the piezo is the hand, and neither blinds the other. Everything downstream is that same split, elaborated teleoperation, depth detection, automated 4-point probing. Depth detection, automated 4-point probing. This section explains why nanorobotic manipulation composes several non-contact forces instead of relying on one. No single non-contact force spans the whole job, so you compose fields by their dynamic range. Dielectrophoresis is the coarse, many-body hand. It sweeps a whole population of viruses onto an electrode and concentrates them. Optical tweezers are the fine, single-body hand. They grip exactly one and carry it to a target cell. Throughput and selectivity trade off inside any one field, so you stack a high throughput concentrator against a high selectivity gripper. Sensing is the same move inverted. Instead of transporting the target, you transport a fabricated probe, a gel bead soaked in a pH or temperature dye, into place, and you read it optically. On a chip, every hand is a force field. The tool is just another manipulated bead. This section explains why handling something at the nanoscale is governed by a single inversion in the force hierarchy. At the nanoscale, the force hierarchy inverts. Gravity and inertia vanish, while surface and adhesion forces dominate. So the trivial macroscopic act, release, becomes the hard problem. The gripper will not let go of what it grasped. This single inversion generates the whole taxonomy of the chapter, shown in figure 11.1. Because the object, whether a cell, a bacterium, a virus, or a DNA strand, is soft, wet, and submicron, the tool must be chosen by the object. It is chosen under a fixed constraint. It must be non-destructive, automatable, and fully controllable. That constraint splits every method into two families. The first is contact, which includes AFM, cell injection, and SEM and ESEM manipulation. The second is contactless, which includes dielectrophoresis and optical tweezers. The contactless family buys its gentleness by never touching the object at all. Predict the placement of any new technique from where it resolves the release problem. This part explains why techniques for handling tiny objects split the way they do, and what coordinate organizes that split. Rigid nanostructures you grab, living matter you must not. That inversion generates the whole chapter. A cell is soft, wet, and dies in vacuum, so the handling toolbox partitions by what the sample survives, not by what the robot can do. The axis is survival, along two directions, contact versus contactless, and native aqueous versus dry. Every technique lands as a point in that two-axis space. AFM and microgrippers touch. Optical tweezers and dielectrophoresis do not. ESEM keeps the water. Read the partition and you can place a method you have never seen. Ask only what force it applies and whether the sample stays wet. The organizing coordinate is fragility. Capability is not what sorts the space. This section explains how optical tweezers turn cell manipulation into biomechanical measurement. A focused laser holds a dielectric bead the way a spring holds a mass. Glue two beads onto a cell as handles, draw them apart, and the cell's resistance is known in piconewtons, while its elongation is read in nanometers off the image. Invert the pair through a mechanical model, and intrinsic stiffness falls out. The generative move is this: a calibrated actuator is a force sensor. Manipulation collapses into measurement, and stiffness is state. Red cells stiffen as tonicity rises. Leukemic phenotypes separate mechanically, so a single mechanical number becomes a disease marker. The book's manipulator here is made of light, non-contact, and self-reading. This section explains how to measure a cell's stiffness by force, and why that stiffness turns out to matter. Squeeze a cell with a known force. Watch how far it yields, and its stiffness falls out. This is an inverse problem. Deformation under load reads off a hidden material constant. The chapter's move is to make light the gripper. Paired optical traps grab microbeads glued to the membrane and pull them apart, delivering piconewton force with no physical contact, so the tool reaches where no gripper made of matter could. The surprise that shifts your model is that stiffness is a phenotype. Cancerous cells run an order of magnitude softer than healthy ones, and leukemic subtypes separate by mechanics alone. Mechanical response becomes a diagnostic, observable, and the robot tweezers system is simply the instrument built to read it. This section explains how an MRI scanner can be turned into a single instrument that both moves a nanorobot and watches where it goes. A clinical MRI is already a machine that locates things by magnetic gradient. Make that same gradient exert force and the scanner becomes actuator and sensor at once, one instrument closing a control loop inside a living vessel. The bead's ferromagnetic core is pulled by the imaging gradient. The imaging readout reports where it went. The whole chapter turns on one scaling tension. Magnetic force grows with particle volume while the scanner's gradient is fixed and weak. That is enough to steer Martel's micrometer bead through a carotid artery, but far too little at the nanoscale, which is precisely why custom high-gradient electromagnets have to appear at all. This part explains how a single magnetic field can do two jobs at once, and why the chapter treats a hard physical model as an asset rather than a nuisance. One instrument is both eye and hand. The MRI's gradient coils image the ferromagnetic robot and also propel it, So sensing and actuation collapse into a single field. The chapter's move is to refuse the usual split between a clean model and messy reality. Consider the nonlinear forces on a bead dragged through pulsing, non-Newtonian blood against the vessel walls. The usual approach rejects those forces as disturbance. This chapter keeps them as structure to exploit. From that fine-grained model, one derives an optimal trajectory that spares the scarce actuator force the MRI gradients can supply. It then tracks that trajectory with an adaptive backstepping law, which estimates the uncertain physiology as it runs. So model complexity becomes the resource rather than the obstacle. That inversion is what makes any hard, nonlinear model worth keeping rather than linearizing away. Nonlinear model worth keeping rather than linearizing away. This section explains how magnetic fields become the control channel for nanorobots inside the body. Tissue is magnetically transparent. Its permeability matches that of air, so a field generated outside the body passes through untouched and grips a ferromagnetic speck inside. That transparency is the entire permission. No tether, no onboard battery, just actuation reaching in from external coils. At a scale where every rival power scheme fails. The generative move is a decomposition. A magnetic body sitting in an applied field feels two independent handles. The field's direction exerts a torque that aligns it. The field's gradient exerts a force that pulls it. Orientation and translation cleanly split across two properties of one single field. So steering a nanorobot in a bloodstream reduces to shaping the external field. Its uniform part sets the heading. Its gradient sets the thrust. Everything the chapter builds is a way of generating that field precisely. This section explains why a nanoscale machine cannot carry its own engine, and the move the chapter makes to solve it. Shrink a machine down to the nanoscale, and its engine vanishes before the machine itself does. Stored energy scales with volume, so an onboard battery starves as the cube of size. The chapter's move is to externalize the actuator entirely. The nanorobot becomes passive magnetic matter, and everything active, power and steering both, lives outside the body in a shaped magnetic field. This works because the human body is magnetically transparent. Its permeability matches air, so an external field passes through tissue untouched. Field torque aligns the body, and field gradient pulls it. Here is the generative primitive. When the mover is too small to carry its engine, make the medium transparent and drive it from the field. This section explains the structural primitive behind MRI-based nanorobotics. A clinical MRI is already a robot with the robot subtracted. Its gradient coils, built to image, double as the one actuator that pushes a ferromagnetic bead. Here is the generative move. Perception and propulsion share a single instrument, so they cannot run at once. The coils are time-shared, acquire a slice, then push, alternating. The agent carries nothing, not even its own visibility. It is too small to resolve. It is seen only through the oversized field distortion it casts, a magnifying glass artifact far larger than the object itself. Everything robotic, the sensing, the driving, the control, has migrated out of the particle and into the scanner that hospitals already own. That externalization is the thesis. The 15 techniques only close the loop around it. On techniques only close the loop around it. This section explains how one MRI scanner performs 3 jobs at once. One machine does 3 jobs. The clinical MRI scanner already builds images by imposing gradient fields that make position readable as precession frequency. Those very gradient coils, redirected, push a ferromagnetic agent through tissue. Seeing and steering share hardware. Time multiplexed. There is no bespoke actuator, only a scanner taught to alternate between imaging and propulsion. The agent is found by its distortion rather than its size. A ferromagnetic speck warps the surrounding field far past its own dimensions, a magnifying glass effect that renders a subvoxel object visible. The chapter's role in the arc is this fusion. The hospital's existing imaging modality becomes the actuation substrate for MRI-guided nanorobotics. Detect the artifact, track it, then propel it, all on the machine already in the room. All on the machine already in the room. This part explains how a therapeutic bacterial nanorobot is built by theft rather than by construction. The design principle is theft. Rather than fabricate a nanoscale motor, you commandeer one that evolution has already perfected. A magnetotactic bacterium with propulsion and sensing and cargo bay fused into a single cell. The external magnetic field never drives it. At this scale, the force a field exerts on a body is negligible. The field only orients the cell, the way a compass needle turns, while the cell's own flagellar motors do the swimming, and its native aerotaxis homes in on the oxygen-starved tumor core that blood-borne drugs can never reach. Steering and propulsion are cleanly split, and the target's defining pathology, its hypoxia, is precisely the gradient the swimmer chases. The tumor's own weakness becomes the homing beacon. This part explains how magnetic microrobotics hits a physical wall at the smallest scales and the move that gets past it. Below roughly 2 micrometers, the physics stops cooperating. No clinical magnetic gradient can push a synthetic carrier that small through a capillary. Martel's move is to stop miniaturizing the machine and to exact an organism already tuned to the scale, the MC1 magnetotactic bacterium. It self-propels by flagella at about 4 piconewtons of thrust, and it carries an iron oxide magnetosome chain that behaves as iron-iron oxide magnetosome chain that behaves as a compass needle Krauss. You no longer drive the robot. You point it, tilting a weak field to aim a living propeller. The generative pattern is this. Once the fabrication target drops beneath the actuation floor, the cheapest actuator is a cell that already solved the problem, and the engineered part collapses to a steering interface onto biology. This section explains how a swarm of nanorobots could diagnose early cancer as an evidential verdict rather than a single reading. No single sign convex. A precancerous state betrays itself only through the conjunction of 3 individually innocent clues: local hyperthermia, a glut of lactic and pyruvic acid, and depressed pH, a combination that healthy tissue never sustains together. Serafulini and Amato cast this as detective work. The organism is the scene of the crime, the tumor is the perpetrator, and a swarm of blood-borne nanorobots is the detecting corpus. Each agent patrols one capillary's diffusion basin and gathers circumstantial evidence too weak to accuse alone. Diagnosis becomes an evidential verdict. Belief is assembled from clues that co-occur and persist, not read off one decisive biomarker. The generative move is to buy reliability from the simultaneity of cheap, redundant, weak signals, rather than from the sensitivity of one strong signal. The crime is inferred, never directly seen. This section explains how the chapter detects a tumor when no single sign is decisive. No single molecule betrays a tumor. The immune system itself cannot separate malignancy from a muscle mid-exercise, since both run hot, hypoxic, and acidic. So the chapter abandons the smoking gun, one decisive marker, and turns instead to frame evidence, identity inferred from the conjunction of 3 individually innocent clues: hyperthermia, hypoxia, and low pH, persisting together in one place. Each clue is ambiguous alone. Their coincidence is improbable by chance. A swarm of blood-borne nanorobots plays detective, each one feeling its own capillaries neighborhood, clustering where all 3 co-occur to raise the alarm. The primitive is this: where no single feature decides, read identity, off the joint, improbability of ambiguous signs. This is forensic inference, the detective's method of building a case from converging clues rather than recognizing one telltale mark. This section explains why DNA is the one place where a robot's design, its body, and its controller stop being separate things. Everywhere else, a robot keeps its blueprint, its body, and its controller in separate materials. DNA collapses the 3 into one. The sequence is simultaneously the design, the structure, and the program of motion. The whole discipline runs on a single primitive, Watson. Crick, complementarity, where A pairs with T and C, pairs with G, is a lookup table. Specificity means a strand binds only its reverse complement. So addressability is complementarity. Choose the letters and you have programmed which pieces meet, and therefore the geometry that self-assembles and the state changes that follow. The same binding rule that folds the object, pushed by strand displacement, enzymes, or a shift in pH, is what makes it walk, switch, or grip everything downstream. The walkers, the tweezers, the nanomachines, is this one move, iterated. This section explains how DNA becomes a programmable machine. You program that machine by writing a string. That is the whole move of DNA nanorobotics. The material is its own blueprint. Watson and Crick pairing, where A binds T and C binds G, makes complementarity a deterministic binding rule. So choosing sequences chooses which segments latch to which. Design collapses to sequence design, and the test tube does the compiling, folding the strands into a target geometry as it cools. Because the same rule governs the dynamics too, a strand can displace another, an enzyme can cut, pH can unlatch. You get not just static shape, but state changes, walkers, tweezers, conformational switches. The chapter's payload is this equivalence between a programmable string and a physical device. Predict the next instance yourself. Any behavior you can encode as a hybridization contract, DNA can be made to enact. This section explains the one primitive that makes DNA self-assembly work. Stop placing parts. Encode which parts stick. Complementary base pairing turns a DNA strand sequence into an address. 2 surfaces bind only when their grafted single strands are Watson-Crick complements, so a string over a 4-letter alphabet becomes a programmable glue, one whose number of mutually orthogonal bonds grows with length. Self-assembly is then thermodynamics searching for the configuration that satisfies every address. The chapter's whole argument reduces to making that glue trustworthy along 2 axes. The first is stability. The bond survives its environment. The second is specificity. Only the intended pair recognizes. Everything downstream, the AFM force measurement, the sequence design algorithms, exists only to measure and tune those 2 knobs. This section explains how complementarity turns sticking into something you can address. Complementarity makes adhesion addressable. Because each strand binds only its Watson-Crick complement, coding two surfaces with matching sequences turns the question of which part sticks to which into a string. The bond, which the authors call DNA Velcro, becomes a code you write. Where adhesion used to be a force you shape, here strength and selectivity fall out of the chosen sequence and the temperature. That is the chapter's move for the book's arc. DNA earns its place in a nanorobot as programmable glue rather than as structural scaffold, self-assembly recast as self-addressing. Everything downstream is predictable from this one inversion. The two questions left are how strong a single address is, its stability, and how unconfusable it is, its specificity. This section explains how a molecular motor, too small to wire, can still be controlled by moving its command input out into the surrounding fluid. The bacterial flagellar motor is only about 45 nanometers across, and it spins near 100% conversion efficiency. There is no control port you can solder to, so its command input is externalized into the fluid. The flagellar motor's rotational speed is a function of the local ion motive force, the sodium ion gradient across its membrane. Set the concentration at the cell, and you set the torque. Fukuda's nano and micro dual pipettes do exactly this. They discharge sodium-rich and sodium-free streams onto a single E. coli, switching between them for transient speed changes and balancing their flow rates for a held steady state. This tunes torque on the order of about 10 to the second power. The primitive. When an actuator is too small to address, move its set point into the environment, one of nature's strongest nanomotors, and it still swims. This section explains the core move of Chapter 20, Rent, Don't Build. Instead of fabricating a nanomotor, you commandeer the bacterial flagellar motor. It is already nearly 100% efficient, self-repairing through metabolism and self-replicating for free, and you steer it from outside. The surprise that makes external control possible is this: the motor speed tracks ion motive force, but homeostasis pins the inside ion concentration constant, so the external concentration becomes the single free variable, a throttle you write in chemistry. Two pipettes paint that local environment, one dispensing a sodium ion-rich solution and one a sodium ion-free solution. This is what Chapter 20 contributes to the book's biohybrid actuation arc. The control surface is the fluid you surround the machine with, not the machine itself.